Hello and welcome back to another quick and dirty science video. Before we get started, I want to make it clear that this isn't a guide for you to pick a bow. If you want to know more about that, you'll have to look at someone who's actually an expert in archery. I'm simply looking at the draw weight of bows from a science and engineering perspective, which is my area of, well, above average understanding. This all started with a video by Historical Archery, where Jack was shooting a 240-pound longbow. If you call this shooting. Oh, God. I'm just kidding, of course. I'm not dumb enough to mock a guy who regularly shoots a 140-pound warbow. Anyway, in the comments of the video, a viewer asked if it was true that bow performance dropped off steeply after you hit 150 pounds. Jack responded saying pretty much yes, that while heavier bows give you more momentum, they start to plateau. He also mentioned that he would like to see tests with more scientific equipment. I would like to see that too, but in the meantime, I can give you a scientific explanation in place of a test. So the first thing we need to do is develop a relationship between the draw weight of the bow and the energy stored in the bow, which for once is easier than it sounds. You might remember from physics that energy is force times distance. So if we treat a bow as an ideal spring, meaning that the force increases linearly with distance, the total energy stored in the bow will simply be 1/2 of the draw weight times the draw distance. Quick side note, I'm going to be using foot-pounds for energy because archery still uses US customary units, but everything will be converted on screen. Now, if we assume that the draw length is constant, which is pretty reasonable for archery, we'll get a simple linear relationship between energy and draw weight. This makes it seem like there shouldn't be a plateau. More weight means more energy, so heavier bows always do substantially more damage, right? Well, it's actually not that simple. To explain, let's look at Jack's bow. It reaches 240 pounds at 32 inches, meaning it stores 320 foot-pounds of energy. Actually, hang on here. While I was editing this video, I realized I actually messed this up. I used the draw length of the bow as the distance the string traveled, but that's not actually true. The draw length is the distance between the archer's hands at full draw, but before you draw the bow, there's already some distance between the belly of the bow and the string. So we actually need to subtract this brace height from our draw length, and that will give us the actual distance that the string travels. For longbows, this ranges between 7 and 9 inches. I went ahead and used 7 just as an estimate, and that gives us a much lower energy of about 250 foot-pounds. So with that said, let's get back to the video. You're just going to have to remember that some of these numbers aren't exactly correct. I was surprised to find that this is basically the same energy as a 9mm bullet. However, the 9mm is a small pistol round. Even a weak rifle like the AR-15, which shoots .223, produces much more energy, typically reaching about 1,300 foot-pounds. More powerful hunting rounds like .270 Winchester get much closer to 3,000 foot-pounds of energy. That's almost 10 times what this bow can do. So why am I talking about firearms in this archery video? Well, it's to explain the difference between energy and momentum. A while back, I made some ballistics gel and shot it with a .270. In slow motion, you can see it basically explodes when the bullet hits it. The bullet sends a shockwave through the entire thing, ripping up all of the gel and even breaking the board that it was sitting on. This shows that bullets do a lot more than just punch holes in things. All of this extra damage being done is the result of the bullet's very high energy content. Arrows simply don't have this kind of energy and they can't do that kind of damage. They are more or less punching holes in their targets. This all means that energy isn't a good indication of how effective a bow can be. Instead, we need to look at the momentum of the arrow. So let's have another flashback to physics. Energy is 1/2 of the mass times the velocity squared, and momentum is simply the mass times velocity. Assuming the mass of the arrow is constant, we can really just look at the velocity terms. First, energy. Because the v is squared, doubling velocity will quadruple energy. But we're actually going backwards from energy to velocity, so that relationship actually works against us. Doubling our energy only increases the arrow's velocity by about 70%. This also means that the momentum of the arrow is only increased by 70% whenever we double the weight. So, plotting this on two graphs, we see that while energy increases linearly with draw weight, the momentum starts to plateau, just like Jack said in his comment. Now, there is, of course, more at play here. A more powerful bow means that the limbs will be heavier, which actually makes the bow less efficient. Remember, when an archer releases, the arrow moves, but so do the limbs. This takes away some of the energy which would otherwise go into the arrow. If you make the arrow heavier compared to the limbs, that means that the arrow will absorb more energy, making the whole thing more efficient, and this will increase your total momentum. However, this does mean a slower arrow, which takes away some of your range even though you're carrying more momentum. There's also all kinds of different bow shapes, which of course affect your efficiency. I wasn't able to find any hard numbers in what was an admittedly brief search. But going back to Jack's bow, the fact that it's not 100% efficient means that it's probably not actually going to match a 9mm. And of course, some bows are less linear springs than others. Here's a graph from a longbow performance project, which I'll link in the description. The graph clearly shows that while some bows are fairly linear, others have much more interesting behaviors. So there's definitely still a need to compile some data on longbow performance at different draw weights to see how all of these other variables can affect the data. I would expect the plateau to actually be worse than this analysis showed just because of all these other issues I've mentioned which come up at higher draw weights. This wasn't actually a very difficult test to do. You just need to get the speed and mass of the arrow, multiply those together, and that gives you the momentum. To make the math easier, I'd recommend doing everything in grams and meters per second. Though if you know what you're doing, it is possible to convert. So really, all you need to do is find a bunch of people with different weight bows, get several shots from each of them to average together, then you can plot those values out on a graph. You'll probably get something a lot like this. But anyway, that's where I'm going to wrap up this video. Hopefully I'll be uploading more often now that I'm finally done with the worst semester of the aerospace engineering curriculum. But for now, I'm Kanhathi, and I will see you in the next video.